Parallel plate capacitor is the most basic form of a capacitor. You do have a spherical capacitor as well with a hollow sphere. But when we talk about a parallel plate capacitor, we know that the capacitance can be expressed basically in the form of area and the distance between the plates. But if we talk about a spherical or any other shaped capacitor, obviously its expression is slightly in the complicated side. Now, when we talk about a parallel plate capacitor, obviously you will not have just a single capacitor. You would have seen in the motherboard of TVs and other computers, there are multiple capacitances. So obviously you need to know when you connect multiple capacitances either in series or in parallel, how you get the net value of capacitance. How do you determine how much the capacity should be? So let's try to learn about that.
Now, as discussed, we'll first be discussing about the parallel plate capacitor. So let's understand about what exactly is a parallel plate capacitor. To put it precisely, let's say you have these two parallel plates. You have some charge that has been distributed across it, so it's going to be charged per unit area. So you'll have one having a plus sigma, that will be having a minus sigma. The electric field is going to be constant throughout this, and there's going to be a potential difference that is going to be induced. So let's try to understand more about it. So when we talk about a parallel plate capacitor, to put it precisely, you just have two parallel plates. One will be having a positive charge, the other will be having a negative charge. Obviously, how much is the amount of charge that you are going to store is also going to depend upon how much is the area. So charge per unit area is what is going to be very, very important. So what we are going to write down here in this case is the following, that we know that charge is going to be given by charge per unit area sigma into the area, right? And here, so this is what we have. Further, you know that the potential difference between these two plates is going to be dependent on the potential on the charge itself. So that is going to be given by 1 over 4 pi epsilon naught into the charge divided by the distance between the two plates. So if I say d is the distance between the two plates, correct? So using this, if I want to find out c, so c will be equals to q over v. So if we find this out, so what will we get? We'll get 4 pi epsilon naught into d, that will we have. So that is for the v, I'm sorry. And in the numerator, you will have q. Oh, just a minute. Let me correct this. So let me write this as q over v first. So q over v is going to be equals to 4 pi epsilon naught d. So the value is, in this case, is going to be, I'll explain what exactly is that and what exactly I have got here. So 4 pi epsilon naught d is you will get in a general case. But if you have the area of cross section that is going to be represented, so in that case you will represent q as equals to k epsilon naught into d. K epsilon naught a into divided by d. So k is nothing but the dielectric constant that we have. Going further on this, if I have to find out how much has been the charge that has been stored, obviously when you connect them in series, the charge that is going to be there is going to be constant. It's just the potentials that are going to be added up. As a result, since we know that the charges are the same and they are going to be dependent on the potentials, so each will have the different capacitance. So let's understand it this way, that C1 V1 is equals to C2 V2 equals to C3 V3. So this way we just equate the charges, and as a result we can also find out the total sum. The total sum is going to be given by V1 plus V2 plus V3. So if I just add it up, so we'll say that the total charge divided by the total capacitance in series is going to be given by, because this is how you are going to add it up, so V is going to be given by Q by C. So we'll get Q by CS, which is going to be the, CS is going to be the net series capacitance. So this is going to be Q by C1 plus Q by C2, Q by C3. And since the charges are exactly the same, so this is the net expression that we'll get when the capacitances have been connected in series. Further, if you have to understand it, how exactly it is going to be there, you can see that the charges are going to be added up because the potentials being the same. So if the charges are going to be added up, so we'll say the net charge is going to be equals to Q1 plus Q2 plus Q3, right? But Q is what? C into V. So we can say then net capacitance is Cp, let's say, into V. That's going to be equals to C1V plus C2V plus C3V. So if I get rid of the factors V, so we'll get Cp as equals to C1 plus C2 plus C3. So this is the net result that we'll get. Now let's try to attempt a problem based on this. So what we have, a parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. So the capacitance is given as H into 10 raised to the power minus 12. What will be the capacitance if the distance between the plates is reduced by half? We know that the capacitance is given by epsilon naught A divided by D, and in a generic case it's going to be K epsilon naught A by D. Okay. Now if I say that initially there is no capacitance, there is no dielectric constant. So if I have to take a ratio, what I will say, C1 by C2 is going to be equals to K1 A1 divided by D1 into D2 divided by K2 into A2. So that is what we have. So if I solve this, so K, initial value of K is 1, which is not given. Initial area, if I take that to be A, initial distance between the plates is D. Then if I say that the distance between the plates is reduced by half, so this becomes D by 2, and the space between them is filled with a substance of dielectric constant 6. That means the area isn't changing. So, but the dielectric constant has a value 6. So what will we get as a result? You can simply say that C1 by C2 is nothing but, this is going to become 1 by 12. The rest of the factors remaining constant, C1 by C2 is going to be 1 by 12. Moving on, if we try to understand it here, what do we say? Explain what will happen if in the capacitance a 3 mm thick mica sheet of dielectric constant 6 were inserted between the plates while the voltage supply remained connected after the supply was connected. Okay. So in this case, when the voltage supply is already connected, I'm just going to give you a hint in this case. What is going to happen here, if I'm going to insert a dielectric constant 3 mm thick mica sheet. So this is what is going to be 3 mm, okay, and the dielectric constant being equals to K is equals to 6. Further, the distance between them is going to be D. So what you have, you basically can say that you have two capacitances like this, one having a dielectric, other without a dielectric. So this is going to be having a length that's going to be equals to D minus 3. This is going to be having a thickness that is equals to 3. Both of them will have the same area of cross section. Since they are in series, so we'll have to use the series formula. So series CS, if I say, since there are only two capacitance, so if I say C1 is a capacity here, C2 is a capacity here, so we'll say C1 C2 divided by C1 plus C2. That is what we have. Going further, let's move on to the next page. So if I have to write it, so C1 is just going to be equals to epsilon naught A divided by D minus 3, and C2 is going to be equals to epsilon naught A divided by 3 with a dielectric constant 6 in it. And as a result, the net of this, so this is, I'm only solving for the first part because the charge is going to remain same. Please understand that. So the net of it is going to be given by epsilon naught A divided by D minus 3 into 6 epsilon naught A divided by 3 whole divided by epsilon naught A divided by D minus 3 plus 6 epsilon naught A divided by 3. So this is going to give me the net series capacitance. Moving back, it says after the supply was connected. So if this is the case, in this case the charge is going to be changed. So you have to first find out how much was the charge change, how much was the initial value of the charges, and when you connect it next, then how much is going to be the potential difference that is going to be produced. Okay, so there are two different cases, so try to understand it in a similar way.
Students, we learned about how to combine capacitances in series or in parallel. When you connect them in series, obviously you see that it's a kind of an inverse relation to that of resistance, whereas when you connect them in parallel, again it's an inverse relation. So when you connect them in parallel, you just need to add up all the capacitances, n number of capacitances, you just add them up. If they are in if they are in series, you need to inverse each of them and then add up. That's going to give you the net resultant. If you have a mixed combination, obviously it's going to be accordingly figured out. Further, when you place any dielectric within a capacitor, within the plates of a capacitor, it has to be found out because that any presence of a dielectric would have a dielectric strength. We have found out what is the relation for that. Dielectric strength increases the capacity of the capacitor. So higher is the dielectric strength, higher is going to be the amount of charge that can be stored in that particular capacitor. So that is what is the basic combinations that we understood for the case of capacitor. Stay tuned for more on that.